Okay, in this video, I want to touch on something. It's a little bit of a stats nerd kind of topic, but I want to talk to you about base rate. So base rate is actually something to think about, not just in um, major neurocognitive disorders, although it plays a part in that, but also in every mental disorder. It has to do with what's the probability that the event has occurred. Um, so again, base rate refers to the probability of an event occurring. Prevalence rates tell us of the base rate. So they are the base rate for mental disorders. And it's actually crucial to consider base rate when you diagnose. And I want to explain what I mean. So consider the following situation. You want to determine whether someone who is 66 years old has Alzheimer's. Now, imagine at 66 years old that 2% of the population has Alzheimer's. Kind of imagine that you want to test everyone at age 66, sort of like a colonoscopy. You do a standard test where you ask every person. And imagine that you have a test that correctly identifies people with Alzheimer's 96% of the time. So it has 4% false negatives. And that for those without Alzheimer's, it correctly identifies they don't have Alzheimer's with a 6% false positive rate. Okay, so um, let me say it again. You have if the person has Alzheimer's, this test will say, we'll give them a result saying yes or no. Yes, they have Alzheimer's, or no, they don't. The conclusion, yes, they have Alzheimer's, it will apply to the person 96% of the time if they do have Alzheimer's. 4% of the time, they can have Alzheimer's, and the test says no, they don't have Alzheimer's. The test, you could also use it with people without Alzheimer's, and most of the time it's going to say no, they don't have Alzheimer's, and so 94% of the time it'll say that, and it'll be correct. But 6% of the time it'll be wrong, and it'll be a false positive. It'll say they have Alzheimer's when they don't. Okay, now let's imagine a situation where you get a positive result. What is the likelihood that this person actually has Alzheimer's? So you get a positive result. What's the likelihood they have Alzheimer's? Is it 4%? Is it 6%? Is it 2%? What is it? Is it 96%? 94%? Well, none of the above. It's a little bit of a math problem. It's actually 25%. So you get a positive result. You've tested someone and you get a positive result. The likelihood that they actually do have Alzheimer's is 25%. Now, if that sounds very low, well, you're not wrong. But it's actually the accurate number. I'll unpack it. So let's say you have 10,000 people, 10,000 66-year-olds. Now, 200 of those will have Alzheimer's. 9,800 will not have Alzheimer's. So the likelihood that you'll get a true hit is actually, well, 200 times 0.96. So 96%. It accurately identifies them as having Alzheimer's. So 192 people out of the 200 will be identified as having Alzheimer's. That's good, right? That seems like it's you missed 8 people out of the 200, but okay, that happens. Now, there's also the possibility of a false positive. This could be a false positive, right? Well, if you think about it, there are, sorry, where is it? It's 9,800 people that don't have Alzheimer's in this population. So what you can do here is take well, you could do this in different ways. You could take the 0.98, or you could just take out the 9,800 people and say, well, there's a 6% chance that they could be falsely identified as having Alzheimer's. So you actually come up with 588 out of the 9,800 will they'll say that they have Alzheimer's. Well, when you think about that, 588 out of 9,800, it's not a high number. But when you compare that to the 192, so total out of the 10,000 people, you have 192 plus 588 people that will be identified as having Alzheimer's. Only 192 of those actually have Alzheimer's. So there's 780 people that get identified as having Alzheimer's, right? 588 false positives, which again is not a high number. It's only 6% of the 9,800. But when you compare that to the 192 that did have Alzheimer's and did get identified as having Alzheimer's, that's pretty low. So 192 out of 780 is about 25%. So we have a problem. If you try to identify a rare condition, now, Alzheimer's isn't that rare, but again, Alzheimer's at 66, fairly rare. And if you try to identify a rare condition with an imperfect assessment, you're liable to have a lot of false positives. So, I mean, there's ways that you can work around this. You could raise the bar up so that there's fewer false positives. But of course, that means you have potentially more false negatives. But it just speaks to the difficulty of making a diagnosis, that you always have to think when you're making a diagnosis, how common is this disorder? If it's common and you get a result that says, yes, they have it, you can be fairly confident that yes, they have it. But if it's a rare condition and you get feedback, if you say, wow, this looks like this rare condition, you always want to second guess yourself and really question, how accurate is this assessment? How accurate is this test? So kind of similarly, if you talk about identifying a terrorist, right? You might have a test that is able to identify a terrorist and say, this is a person who is a terrorist, or this is not a person who is a terrorist. The difficulty of doing that with a large group of people is that most people aren't terrorists. And so if you're trying to identify this rare case of a terrorist, you are liable to have a lot of false positives, a lot of people that mistakenly get identified as being maybe a terrorist that aren't actually. So base rate's really critical when you think about diagnosing, actually for a bunch of different things. I just wanted to touch on it briefly as we wrap up this class. So hopefully that's interesting to those of you who are stats nerds. All right, all in there.